Stars. We look at them every night, scattered across the darkness like tiny sparks, so distant and so silent that it's easy to forget what they really are. Each one is a massive burning sphere of gas, larger than planets, older than civilizations, and more powerful than anything we can create. Yet when we look up, they appear small, almost harmless, just dots in a quiet sky. But the truth is far more overwhelming. The number of stars in the universe is so large, so beyond human imagination, that even trying to express it in words feels impossible. And still, scientists have found clever ways to estimate that number, revealing a cosmos overflowing with light, on a scale we can barely understand. The first step to answering the question begins with something familiar: the night sky as seen from Earth. On a clear night, far from city lights, the human eye can see around 3,000 stars. That number feels large, but it is nothing compared to the true population of the cosmos. 3,000 is not even a fraction of 1%. It is not even close. Imagine walking into a library that contains every book ever written, and you can only see 3 books on a shelf. That's how limited our eyes are when we look at the stars. The universe hides almost everything, not because it wants to, but because the scale of space is too enormous for our senses. The next step is understanding our own galaxy, the Milky Way. This vast collection of stars surrounds us like a cosmic island, stretching 100,000 light-years across. Our sun is just one star among hundreds of billions. For years, scientists estimated that the Milky Way contained around 100 billion stars. Then improved measurements suggested 200 billion. Later observations hinted that the number could be even higher, possibly 400 billion, maybe more. The truth is we don't know the exact number because the galaxy is full of dust, hidden stars, faint dwarfs, and regions we still cannot see clearly. But even the lower estimates tell us something extraordinary. The Milky Way alone contains more stars than the number of grains of sand you can hold in your hand. But the real shock comes when we step outside our galaxy. The universe is not made of one galaxy. It contains hundreds of billions of them, each with its own population of stars. When the Hubble Space Telescope captured the famous deep field images, tiny patches of sky observed for days to reveal the faintest objects, we learned something astonishing. A small piece of sky, the size of a grain of sand held at arm's length, contained thousands of galaxies. If such a tiny area holds so many galaxies, then the entire sky must hold hundreds of billions. The universe suddenly expanded in our minds, not by a small amount, but by an unimaginable factor. Once we combine the average number of stars per galaxy with the total number of galaxies, the true scale begins to emerge. If a typical galaxy contains 100 billion stars, and there are hundreds of billions of galaxies, the total number of stars becomes a number so large it almost loses meaning. The estimated count reaches into the range of 10 sextillion to 1 septillion. That is a 1 followed by 21 to 24 zeros. A number so large that even if you attempted to count 1 star every second, you would still never come close. Not in a lifetime, not in all of human history, not even if every person on Earth counted continuously forever. But the story becomes even more overwhelming when we consider how much we still don't know. Telescopes observe only the visible portion of the universe, known as the observable universe. This sphere stretches 46 billion light-years in every direction. But beyond that horizon lies more universe we cannot see. Light from those regions has not had enough time to reach us. If the cosmos continues indefinitely beyond what we can detect, then the number of stars may not be just huge, it may be infinite. Our current estimates may represent only a small slice of the cosmic ocean. Even within the observable universe, not all stars are visible to telescopes. Many are too faint. Red dwarfs, the smallest and most common type of star, burn dimly and live for trillions of years. They are everywhere, far more numerous than stars like our Sun, but they barely emit enough light to be noticed. Some stars hide behind thick clouds of dust. Some are surrounded by star-forming regions so dense that light struggles to escape. Others sit in galaxies on the edge of detection, so faint they appear only as hazy smudges. Every improvement in telescope technology reveals more stars, increasing the total count. And stars are not evenly distributed across the universe. Some regions contain dense clusters where stars are packed together tightly. Others are sparse with enormous voids where stars are rare. Some galaxies are small and contain only a few million stars. Others are giants with trillions. These differences make counting stars even more complicated. It's like trying to count raindrops in a storm. Some drops fall close together, others far apart, and many escape detection entirely. The universe also changes over time. New stars are born every second as gas clouds collapse under their own gravity. Old stars die, exploding as supernovae or shrinking into white dwarfs and neutron stars. The star count is not static. It is dynamic, evolving, shifting. The observable universe contains stars at every stage of life, from newborn stars glowing in bright nebulae to ancient stars nearing the end of their long journeys. This constant cycle means the universe is alive with creation and destruction on a cosmic scale. Another fascinating factor is how stars group together. The Milky Way is organised into spiral arms, dense regions where star formation is active. Globular clusters are tightly packed spheres containing hundreds of thousands of old stars. Dwarf galaxies revolve around larger galaxies, each with its own population. The structure of the universe is not random. It forms patterns shaped by gravity, dark matter, and cosmic history. These patterns affect how stars form, how many form, and how they spread across the cosmos. Understanding these structures helps scientists estimate the number of stars with more accuracy. Then there is the concept of cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. If inflation expanded space much farther than we can observe, then the regions beyond our reach may contain countless galaxies, each with billions of stars. The observable universe may be only a small portion of a vastly larger reality. If that is true, the total number of stars becomes a quantity so large that the human mind cannot hold it. Numbers like 1 septillion start to feel small. The universe might contain more stars than atoms in some planets. It may contain more stars than any number we currently use in science or mathematics. Even the methods scientists use to estimate star counts reveal how far we still have to go. Astronomers analyse galaxy brightness to determine how many stars they contain. They examine spectral data to understand star distribution. They study star formation rates and galaxy evolution. But despite all these tools, every estimate comes with uncertainties. Some galaxies are too distant to measure accurately. Some are too faint. Some are too distorted by gravitational lensing. And some may exist where our instruments cannot yet detect them. Each refinement in data improves our understanding, but the number of stars may never be known with perfect precision. But maybe the exact number is not the important part. What matters is what that number represents. It represents possibilities. It represents countless solar systems, countless planets, countless environments where life could exist. If the universe contains a septillion stars, and if even a tiny fraction of those stars host planets, then the number of planets is beyond comprehension. And if even a tiny fraction of those planets are habitable, then the potential for life fills the universe like scattered seeds waiting for the right moment to grow. This perspective does something powerful. It breaks the illusion of isolation. It turns the night sky from a collection of distant dots into a vast network of suns, each one a beacon of potential. We begin to understand why astronomers look at the sky not with fear of emptiness but with excitement. The universe is overflowing with stars. It is overflowing with opportunities. It is overflowing with light. As we continue exploring, our telescopes become more advanced. The James Webb Space Telescope already reveals stars and galaxies formed only a few 100 million years after the Big Bang. Future observatories will see farther, sharper, deeper. With each discovery, the star count will grow. New galaxies will emerge from darkness. New estimates will climb. And our understanding of the universe will expand along with them. Yet even with all this knowledge, standing under a dark sky and looking up remains one of the simplest ways to feel the scale of the universe. The stars we see with our eyes represent only a tiny fraction of what exists, but that tiny fraction is enough to inspire wonder. Behind every visible star lie billions more. Behind every patch of darkness lies entire galaxies hidden from sight. The sky is not empty, it is full beyond anything we can imagine. Trying to count all the stars in the universe is like trying to count all the grains of sand on every beach on Earth, and then multiplying that by billions. The number escapes us because it belongs to a scale we are not built to understand. But the attempt to understand it is what makes the question meaningful. It stretches our minds. It humbles us. It reminds us that the universe is not small, and neither are we, because we are capable of asking such questions in the first place. The question of how many stars exist in the universe leads naturally to another question. How did the universe create so many in the first place? Stars did not appear all at once. They were not scattered instantly across space. They formed through a long sequence of events that began with the very birth of the universe itself. And to understand why the cosmos contains such an unimaginable number of stars, we have to follow the story back to the beginning, a time when there were no galaxies, no planets, no elements, and no light at all. The universe was a hot, dense, turbulent place, and everything we see today unfolded from those early conditions. In the first moments after the Big Bang, the universe expanded at a speed far beyond anything we can observe today. This expansion was so rapid that it stretched space itself, flattening it and smoothing it out. But despite this smoothing effect, the early universe was not perfectly uniform. It contained tiny fluctuations, small regions that were slightly denser than their surroundings. These small differences, almost too small to imagine, became the seeds of everything that would form later. Without these early fluctuations, the universe would be an empty fog, instead of a cosmic landscape filled with stars and galaxies. As the universe cooled, hydrogen and helium, the simplest and lightest elements, formed. These gases filled space evenly, creating a cosmic ocean stretching in every direction. But the same tiny fluctuations in density that existed at the beginning allowed gravity to take control. Gravity works slowly, but over long periods, it becomes the most powerful force shaping the universe. Regions with slightly more matter began to pull in surrounding gas. Over millions of years, these small differences grew larger. The densest regions became clouds of gas, then clusters, then massive structures that would eventually become galaxies. This entire period is called the cosmic dark ages, a time before the first stars ignited. The universe contained gas but no sources of light. For hundreds of millions of years, everything remained dark. But the darkness didn't last forever. As gas continued to collapse under gravity, temperatures increased in the centers of forming clouds. When enough mass gathered and pressures grew high enough, nuclear fusion ignited. The first stars were born, and the universe lit up for the first time. These first stars were nothing like the stars we see today. They were enormous, much larger than our sun, because the early universe contained only hydrogen and helium. Without heavier elements to cool the gas, clouds collapsed into extremely massive stars. These giant stars burned hot, lived briefly, and died explosively as supernovae. Their deaths created heavier elements, carbon, oxygen, nitrogen, iron, and scattered them across space. These elements later became part of planets, moons, oceans, atmospheres, and even living organisms. In this way, the first generation of stars set the foundation for everything that came after. The explosions of these early stars also triggered new waves of star formation. When a supernova exploded, the shockwave pressed surrounding gas together, causing new stars to form. This chain reaction, repeated over and over, the universe became a continuous engine of star creation, each generation giving rise to the next. Over time, as heavier elements accumulated, the stars that formed became smaller and more stable. Many of the stars born in later generations were similar to our sun, or even smaller red dwarfs. These smaller stars burn longer, live longer, and populate galaxies in much greater numbers. This shift in star formation style, from massive short-lived stars to abundant long-lived stars, increased the total number of stars dramatically. While stars were forming, the universe was also assembling galaxies. Gravity gathered billions of stars together into clusters, then into rotating disks and spirals. These galaxies became the cosmic factories that continue creating stars even today. The Milky Way, for example, still forms new stars from clouds of gas. Other galaxies form stars at much faster rates. Some starburst galaxies create hundreds of new stars every year. The speed of star formation varies, but the process remains constant across the universe. Gas collapses, stars ignite, and the cycle continues. Dark matter also played a major role in shaping the number of stars. Although invisible, dark matter makes up most of the mass in galaxies. It forms large halos that act like gravitational skeletons. These halos hold galaxies together and help them form in the first place. Without dark matter, the gas in the early universe would not have clumped together efficiently enough to create galaxies or stars. Dark matter provided the gravitational scaffolding that made star formation possible. The universe's enormous star count owes much to this unseen material. Another factor in producing so many stars is the way galaxies interact. Galaxies collide frequently on cosmic timescales. When two galaxies pass through each other, their gas clouds compress and trigger waves of star formation. Collisions do not stop star creation, they accelerate it. Some of the brightest, most active star-forming regions exist in galaxies that are merging. These collisions can generate billions of new stars in a single event. As galaxies merged over billions of years, the universe filled with more and more stars. Star formation also depends on temperature and density. cold, dense gas clouds collapse more easily than warm, diffuse ones. As galaxies evolve, some develop environments where gas cools efficiently. These cold regions become stellar nurseries, large zones where stars form continuously. The Milky Way contains such nurseries, but some galaxies contain even larger ones. This unevenness creates galaxies rich in stars, and others with few. The universe is diverse, offering different conditions that either promote or limit star formation. Over billions of years, galaxies continue to grow, merge, and evolve. The largest galaxies in the universe today contain trillions of stars. Each of these massive galaxies formed through hundreds of mergers and periods of intense star formation. Their histories stretch back to the early universe, and every stage contributed to adding more stars to the cosmic total. At the same time, many dwarf galaxies formed, small, faint galaxies that contain millions to billions of stars. Although they are small individually, they are incredibly common. For every large galaxy like the Milky Way, there are dozens of dwarf galaxies clustered around it. These dwarfs add significantly to the total star count. Their combined number pushes the total even higher than early estimates suggested. Even today, the universe continues creating stars. In some galaxies, the process has slowed over time because gas supplies are limited. Other galaxies, especially younger ones, still produce stars at incredible rates. The cycle repeats endlessly: gas collapsing, stars igniting, stars dying, and new stars forming from the recycled material. The universe is not static. It is a dynamic, ongoing engine of creation. Understanding why the universe contains so many stars also reveals why it will continue to do so for trillions of years. Small stars, especially red dwarfs, can live for enormous spans of time, longer than the age of the universe itself. While massive stars explode quickly, red dwarfs burn their fuel slowly. They will continue shining long after galaxies, like the Milky Way, have exhausted their gas supply. Even when new star formation slows down, the existing stars will keep the universe illuminated for ages. The quantity of stars we see today is a snapshot of a process that began billions of years ago and continues today. Every star we observe is part of a cosmic lineage stretching back to the earliest moments of the universe. Every star was shaped by gravity, temperature, density, and the chemistry of the gas clouds that birthed it. The total number is not a fixed amount. It is the result of countless cycles of formation and destruction across a universe that spans unimaginable distances. The scale of this process is what makes the star count so incredibly large. Each galaxy is a factory containing billions or trillions of stars. Each region of the universe contains thousands of galaxies. The observable universe contains hundreds of billions of such regions. And beyond the observable universe may lie more cosmic structures, each one adding to the total. The vast number of stars is not a coincidence. It is the natural outcome of how the universe expands, cools, and evolves. As we study the universe with better instruments, new observations constantly reshape our understanding. Telescopes reveal galaxies that were invisible before. They show us star-forming regions hidden behind dust. They detect faint red dwarfs, too dim to see with older technology. Every improvement in sensitivity increases the number of stars we know about. As a result, our estimates grow over time, inching closer to the true, though possibly unreachable, total. The most important lesson from all this is simple. The universe produces stars on a scale that defies imagination. It is not an empty void. It is a vast, fertile environment where gravity continually creates new suns. Stars are the fundamental building blocks of the cosmos, and their overwhelming abundance shapes everything, from galaxies to planets to the possibility of life. Galaxies are the homes of stars, but not all galaxies are equal. Some galaxies shine brightly with trillions of stars, spreading across enormous distances and forming complex structures. Others are faint, small and quiet, containing only a few million stars. This difference matters because when we try to understand how many stars exist in the universe, we must understand why galaxies vary so dramatically. The universe did not give every galaxy the same tools for forming stars. Instead, each galaxy evolved under different conditions, shaping its size, brightness, and star count. By exploring why galaxies hold such different numbers of stars, we get closer to understanding the true scale of the cosmos. The first reason for this variation comes from the initial conditions in the early universe. Right after the Big Bang, matter spread across space in uneven patterns. Some regions had slightly more matter than others. These tiny differences became amplified as time passed. Regions with more matter pulled in surrounding material faster, growing into massive galaxies. Regions with less matter stayed small and formed dwarf galaxies. These early differences in density created the foundation for everything that followed. Even now, billions of years later, galaxies still reflect those early imbalances. Another major factor is the role of dark matter. Although invisible, dark matter makes up most of the mass in galaxies. It forms giant halos that serve as cosmic containers for normal matter like gas and dust. The size of a galaxy's dark matter halo determines how much gas it can attract. Larger halos pull in more gas, allowing for more star formation. Smaller halos attract less gas, limiting how many stars can form. This is why massive galaxies like Andromeda or giant ellipticals can contain trillions of stars, while tiny dwarf galaxies may have only a few million. The invisible structure beneath each galaxy shapes everything about it. Gas availability is one of the most important ingredients in this process. Stars form from clouds of hydrogen and helium. A galaxy rich in gas can continue forming stars for billions of years. A galaxy lacking gas stops forming stars and slowly becomes dimmer as its existing stars age and die. Some galaxies use their gas quickly in bursts of star formation. Others used it slowly. Interactions with nearby galaxies also shape a galaxy's gas supply. Collisions can strip gas away, shut down star formation, or trigger massive bursts of star creation. Gas is the fuel for star formation, but not all galaxies receive the same amount or keep it long enough. Galaxy shape also affects its star count. Spiral galaxies like the Milky Way have disks full of gas and dust, which create an ideal environment for star formation. Their rotating arms compress gas clouds and trigger new stars to form regularly. This is why spiral galaxies tend to be bright and filled with many young stars. Elliptical galaxies, on the other hand, are more rounded and often contain older stars. They have less gas, which means they form fewer new stars. These galaxies are usually remnants of collisions between spirals. When two spirals merge, their gas can become heated and scattered, shutting down star formation. The result is a giant elliptical galaxy filled with aging stars but lacking the gas needed for new ones. Dwarf galaxies tell a different story. These small galaxies often contain only a few million stars, tiny compared to the Milky Way's hundreds of billions. Their small size makes them vulnerable. Nearby large galaxies can pull gas away from them through tidal forces. Dwarf galaxies often orbit bigger galaxies like satellites. As they orbit, they lose gas, get stretched, and become irregular in shape. Without gas, they cannot form new stars. Over time, they fade into faint remnants of what they once were. Yet dwarf galaxies are extremely important because they are the most common type of galaxy in the universe. There may be hundreds of billions of them. Even though each contains relatively few stars, their sheer number adds significantly to the total. Galaxy collisions also influence star counts across the universe. When two galaxies collide, the interaction can compress gas clouds, triggering massive waves of star formation. Entire regions light up with new stars. Some galaxies undergoing mergers form hundreds of stars every year. These starburst galaxies temporarily outshine normal galaxies, producing stars at a rapid rate. Although this phase doesn't last forever, it significantly increases the number of stars a galaxy can have. Many of the largest galaxies in the universe grew this way. Mergers combined their stars, added their gas supplies, and triggered star formation on a scale far beyond what a single galaxy could achieve alone. Environmental factors also influence how many stars a galaxy contains. Galaxies in dense clusters feel strong gravitational forces from their neighbours. These forces can strip gas away or cause galaxies to collide. Some galaxies fall into clusters so fast that their gas is removed entirely, shutting down star formation. Others pass through gas-rich regions where they gather material and ignite new star formation. The environment around a galaxy is constantly shaping its ability to form stars. Galaxies in quiet regions of space may remain stable for billions of years, slowly forming stars. Galaxies in chaotic regions evolve faster and go through more dramatic changes. Another reason galaxies differ so much is their age. Older galaxies have had more time to form stars, grow through mergers, and accumulate mass. Younger galaxies are still building themselves. Some of the oldest galaxies in the universe appear huge and mature, even though they formed quickly in cosmic history. These ancient giants experienced rapid star formation early on, building up massive populations of stars. Meanwhile, younger galaxies are still small, still gathering gas and still forming their first generations of stars. This age difference creates a natural variation in star numbers across the universe. The internal processes of galaxies also play a role. Some galaxies have central black holes that are extremely active. These black holes can heat surrounding gas, preventing it from cooling and forming new stars. Galaxies with very active black holes may stop forming stars early. Others have quieter black holes that allow star formation to continue for longer. The balance between gas cooling and black hole activity influences whether a galaxy produces many stars or remains sparse. The distribution of stars within galaxies is also shaped by cosmic history. Regions with dense gas clouds form clusters of stars, while other regions remain empty. Spiral arms concentrate gas and trigger new star formation. Central bulges of galaxies often hold older stars that have not formed recently. The outer regions of galaxies may contain faint, scattered stars left over from past mergers. Each region contributes differently to the total count, creating a complex internal landscape. As telescopes improve, we see more of this diversity. Some galaxies are extremely faint and difficult to detect, hiding billions of stars behind clouds of dust or in the distant corners of the universe. Others are so bright and massive that they dominate. Their local regions of space Every new discovery adds to our understanding, showing that galaxies vary widely, not only in number of stars, but also in shape, brightness, and behaviour. This variation is what makes estimating the total number of stars so difficult. If every galaxy held the same number of stars, the calculation would be simple. But galaxies differ by factors of hundreds, thousands, even millions. Some galaxies contain 20 stars, others contain 2 trillion. To estimate the total number of stars in the universe, scientists must consider the distribution of galaxies of all sizes, from dwarfs to supergiants. They must also account for galaxies too faint or too distant to see. This complexity is why the estimates keep evolving, and why the true number may be far greater than what we currently predict. Even the universe's expansion influences star counts. As space expands, galaxies move farther apart. This reduces interactions and collisions over time, slowing star formation in many regions. In the early universe, galaxies collided more often, forming stars rapidly. Now star formation has slowed overall, but the vast number of stars already created remains fixed. The universe today is filled with stars formed over billions of years of intense activity. Understanding why galaxies contain different numbers of stars helps us understand the grand structure of the cosmos. It shows us that star formation is not uniform. It depends on dark matter, gas, gravity, collisions, and countless other factors. The universe is not a random collection of stars. It is a complex, interconnected system where galaxies grow, evolve, merge, and fade across time. The shocking variety of galaxies is what makes the universe so rich. Without this diversity, the cosmos would be far less interesting. Some galaxies act as star factories, bursting with new light. Others are quiet relics of ancient cosmic history. Together, they create a universe overflowing with stars, a universe far beyond anything we can count. To understand how many stars exist in the universe, we first need to understand how many galaxies exist. Stars do not float alone in the darkness. They are born, live, and die inside galaxies, vast collections of matter shaped by gravity and cosmic history. But counting galaxies across the universe is just as difficult as counting stars. The universe is enormous, stretching far beyond what we can see. Much of it remains hidden behind dust, distance, or the limits of our instruments. Still, scientists have developed methods to estimate the number of galaxies, and every time we improve our telescopes, the numbers grow. The universe keeps showing us that whatever we thought was a lot is still only the beginning. The first major step in estimating galaxy numbers came from one of the most important images in astronomy, the Hubble Deep Field. When astronomers pointed the Hubble Space Telescope at an empty piece of sky, an area so small it looked like nothing was there, they discovered thousands of galaxies in that tiny patch. This was a turning point. If a seemingly empty region contained thousands of galaxies, then the entire sky must contain hundreds of billions. At the time, scientists estimated around 100 billion galaxies in the observable universe. This number alone was staggering, but it turned out to be far too small. Later, when Hubble captured deeper and sharper images, such as the ultra-deep field and the extreme deep field, even more galaxies appeared. Galaxies too faint or distant to detect before. Suddenly the estimates doubled, then they tripled. Scientists realized that the early universe had far more small, faint, young galaxies than previously believed. Many of these galaxies had merged over time, becoming larger galaxies like the Milky Way. The deeper we looked, the more galaxies we found. Instead of 100 billion, the new estimates became 200 billion. Then it grew again. Eventually, the number rose to around 2 trillion galaxies in the observable universe. This dramatic increase did not happen because more galaxies suddenly appeared. It happened because technology improved. Better telescopes allowed us to see fainter objects. More sensitive detectors captured light that older instruments missed. Longer exposure times revealed galaxies hidden in darkness. The universe did not change. Our view of it did. Each improvement showed us that the cosmos is far more populated than we imagined. Estimating the number of galaxies also requires understanding how they are distributed. Galaxies are not spread evenly throughout space. They gather into clusters, superclusters, and cosmic webs separated by enormous empty regions called voids. These cosmic structures reveal how matter moved and settled after the Big Bang. To estimate galaxy numbers, scientists study these patterns. They simulate how galaxies form, how dark matter shapes their distribution, and how gravity pulls them together over billions of years. These simulations confirm that the number of galaxies we see in deep field images reflects the larger universe, allowing scientists to estimate totals based on small samples. But deep field images capture only one type of galaxy well, the bright ones. The universe contains countless faint galaxies that are extremely difficult to detect. Some are small dwarf galaxies with only a few million stars. Others are distant galaxies whose light has been stretched and dimmed by billions of years of cosmic expansion. Some are so faint they blend into background noise. These faint galaxies are crucial to the universe's star count because they are incredibly numerous. They may contain fewer stars each, but there are so many of them that together they contribute massively to the cosmic total. Newer telescopes have revealed even more faint galaxies. The James Webb Space Telescope, with its powerful infrared vision, can see galaxies so distant and so ancient that Hubble could only guess they were there. Webb has already detected galaxies that formed just a few 100 million years after the Big Bang, galaxies we never expected to find so early. Their existence suggests that galaxy formation began sooner and more rapidly than once thought. This means the universe contains far more galaxies than earlier estimates predicted. One challenge in estimating galaxy numbers is that the universe is constantly changing. Galaxies merge, shrink, grow, and evolve. Some are destroyed in collisions, others lose gas and fade. Some grow larger and become star factories. Because of this evolution, the number of galaxies today is not the same as the number billions of years ago. The early universe had many more small galaxies. Over time, these merged into fewer, larger galaxies. So the total number we see now reflects both creation and destruction. Understanding this cosmic evolution helps us estimate how many galaxies existed in the past and how many still populate the universe today. Another difficulty is the observable universe itself. The universe is expanding, and light takes time to travel. When we look far into space, we are looking back in time. The farther we look, the younger the galaxies appear. This means our galaxy estimates represent different eras of the universe all at once. Nearby galaxies reflect the modern universe. Distant galaxies show us the early universe. Combining these time slices into a single estimate requires careful calculations and models. Despite these challenges, scientists continue refining methods to estimate galaxy numbers with increasing accuracy. Even with all of this, we must remember that the observable universe is only a portion of the entire cosmos. Beyond the observable horizon lies more universe, possibly much more, hidden from our view, because light has not had enough time to reach us. If the universe is truly infinite, then the number of galaxies is infinite as well. If it is finite but extremely large, the number of galaxies could be far greater than what we can detect. This means our estimates apply only to the part of the universe we can see. The rest remains unknown. The true total might be billions or trillions of times larger. Another method scientists use to estimate galaxy numbers involves studying the average density of galaxies in deep field surveys. By counting how many galaxies appear in a tiny patch of sky, then multiplying that density across the entire sky, we create large-scale estimates. These estimates improve with better data. Early studies suggested around 100 billion galaxies. Later studies pushed that number to 2 trillion. Future telescopes might increase it again, showing us that the universe still contains galaxies too faint or distant to see today. Galaxies also come in many shapes and sizes. Giant elliptical galaxies can contain several trillion stars. Large spiral galaxies like the Milky Way contain hundreds of billions. Dwarf galaxies contain millions. Ultra-compact dwarfs contain even fewer. But because the universe contains far more small galaxies than large ones, these faint, tiny galaxies greatly influence the total count. The more we learn about dwarf galaxies, the more we realize they are essential to understanding the universe's true population. The cosmic web shows us that galaxies form along filaments of dark matter stretching across the universe. These filaments intersect at nodes where galaxy clusters form. By mapping these structures, scientists estimate how many galaxies are likely to exist in areas we cannot see. This method further expands our understanding of galaxy numbers and reinforces the idea that the observable universe contains far more galaxies than originally believed. Even gravitational lensing helps reveal hidden galaxies. When massive galaxy clusters bend light from more distant objects, they magnify faint galaxies behind them. This natural magnification reveals galaxies that would otherwise remain invisible. These discoveries add to the growing evidence that the universe is overflowing with galaxies we cannot detect directly. All of this leads to one simple conclusion. The number of galaxies in the universe is enormous, and every improvement in technology pushes the estimate higher. Our current best estimate, around 2 trillion galaxies, may still be too small. Future telescopes may reveal even more, filling the universe with a richness beyond anything that we have imagined so far. The number of galaxies matters because each one holds stars, sometimes hundreds of billions, sometimes trillions, sometimes only a few million. When we multiply galaxies by the average number of stars they contain, the star count explodes into unimaginable territory. Each galaxy is a container of light. Each one contributes another layer to the cosmic population. And the more galaxies we find, the more stars we must add to the total. Understanding how many stars exist in the universe requires understanding how they are made. Every star, no matter how massive or small, begins its life inside a galaxy, born from clouds of gas and dust. But not all galaxies produce stars at the same rate. Some galaxies are full of young, bright stars forming every day. Others have gone quiet, forming almost no new stars at all. Some galaxies explode with star formation, creating thousands of stars in a single year. Others barely create one. These differences explain why the universe contains so many stars, and why the total count continues to rise. Star formation begins with cold gas. In galaxies, especially spiral galaxies like the Milky Way, enormous clouds of hydrogen float quietly between stars. These clouds look empty from afar, but they are full of material waiting to collapse under gravity. When a disturbance occurs, such as a passing star, a shockwave from a supernova, or the movement of the galaxy's spiral arms, the cloud begins to contract. The gas clumps together. The temperature rises, gravity tightens its grip. Eventually, dense pockets form within the cloud. These pockets are the seeds of future stars. As gas continues collapsing, the center grows hotter and denser. When the core becomes hot enough, nuclear fusion ignites and a star is born. Light floods out, heat escapes. The newborn star pushes away surrounding gas shaping its environment. Some stars form alone, others form in clusters with dozens, hundreds, or even thousands of siblings. These stellar nurseries glow with young stars still wrapped in the remains of the cloud that created them. This process repeats constantly across galaxies. The Milky Way still forms several stars every year, but some galaxies far exceed this rate. In starburst galaxies, star formation happens at an explosive pace. These galaxies produce stars 10, 100, or even 1,000 times faster than the Milky Way. Their brightness comes not from old stars, but from swarms of newborn ones, burning hot and bright. Starburst galaxies often form during collisions. When two galaxies collide, their gas clouds crash together, compressing and igniting waves of star formation. The result is a sudden violent surge that creates millions of new stars. Not all galaxies experience such bursts. Some galaxies run out of gas early in their lives. Without gas, star formation stops. These galaxies grow old, their stars fade, and they gradually become dimmer. Elliptical galaxies are examples of this. They contain mostly old stars and almost no young ones. Their gas was used up billions of years ago or blown out during galaxy mergers. They are quiet cosmic graveyards, holding the remnants of earlier star-forming periods. Even though they contain many stars, they do not add new ones to the universe. In contrast, spiral galaxies like the Milky Way have stable, rotating structures that preserve gas over long periods. The spiral arms act as engines that compress gas as they rotate. Wherever the arms pass, star formation follows. This is why spiral arms appear bright. They are filled with young stars born from the passage of the arms through dense gas regions. The Milky Way's calm, ordered structure allows it to form stars slowly and steadily for billions of years. The amount of gas a galaxy holds determines how many stars it can create. Galaxies that gather large amounts of gas early in their lives grow quickly. Others that lose gas, either through supernova winds, black hole activity, or galaxy collisions, form fewer stars. Gas is the limiting factor. Without gas, nothing happens. With too much gas, star formation becomes chaotic and bursts out of control. Temperature also plays a role. Cold gas collapses easily. Warm gas resists collapse. Some galaxies have gas that stays warm due to heating from black holes at their centres. These black holes do not swallow all the energy. They release powerful jets and radiation that heat surrounding gas. This prevents the gas from cooling enough to form stars. As a result, even galaxies rich in gas can fail to create stars if their central black hole is too active. These galaxies remain dim despite having the raw materials for star formation. Star formation also depends on turbulence within gas clouds. If the gas is too turbulent, gravity cannot pull it together. In some galaxies, winds from young stars or supernova explosions stir the gas violently, slowing the birth of new stars. In quieter galaxies, gas settles gently, allowing star formation to proceed smoothly. Another important factor is metallicity, the abundance of elements heavier than hydrogen and helium. Early in the universe, galaxies had low metallicity. Stars formed mostly from pure hydrogen and helium. As stars died and spread heavier elements into space, galaxies grew more chemically rich. This increased metallicity allowed gas to cool faster, encouraging more star formation. Metal-rich galaxies today produce stars more efficiently than the earliest galaxies ever could. This increase in metallicity over time helped boost the total number of stars formed throughout cosmic history. Galaxy mergers are one of the most dramatic triggers of star formation. When two galaxies approach one another, gravity distorts their shapes and compresses their gas. Even before they collide, tidal forces stir the gas and ignite widespread star formation. After they merge, the combined galaxy may experience massive starbursts across large regions. This is one reason the universe is so full of stars. Galaxies have been colliding and merging for billions of years. Every time they do, new generations of stars are born. As galaxies evolve, some reach a state where star formation nearly stops. These galaxies are called quenched. They may have used up their gas or lost it through violent processes. But even these galaxies still contain huge numbers of stars formed earlier. Their contribution to the cosmic star count remains enormous, even though they no longer create new stars. There are also ultra-diffuse galaxies, large in size but containing very few stars. Their faintness makes them easy to miss, yet they exist in significant numbers and must be included when estimating total stars. Some contain only a few million stars spread across a massive volume. Others hide surprising amounts of dark matter. These galaxies defy expectations, showing how varied the universe truly is. On the opposite extreme are giant ellipticals and massive spirals containing trillions of stars. These galaxies dominate galaxy clusters. They grew through repeated mergers and intense star formation over billions of years. One such galaxy can contain more stars than thousands of dwarf galaxies combined. Their presence inflates the total number of stars in the universe significantly. When we count galaxies, we count each one equally. But when we count stars, the giants dominate. Another key insight is that star formation has changed over cosmic time. Around 10 billion years ago, the universe was far more active in forming stars. Galaxies created stars at much higher rates because they contained more gas. As time passed, much of that gas was consumed or expelled. Today, the universe forms stars at only a fraction of the earlier rate. But the stars created in that earlier era remain. The star count we estimate today is the result of billions of years of star formation at changing speeds. Star clusters also add complexity. Some clusters form thousands of stars tightly packed together. Others form loosely bound groups. Some clusters remain stable for billions of years. Others disperse quickly, spreading stars across the galaxy. These clusters contribute to the total number of stars and reveal how varied star formation can be. The Milky Way itself shows how diverse star formation is. Our galaxy has active star-forming regions in its spiral arms, quiet old regions in the bulge, and a halo containing ancient stars. Some parts of the galaxy are star factories, others are relics of early cosmic history. This variety exists in almost every galaxy we observe, and it influences how stars populate the universe. When scientists estimate the total number of stars, they must account for all these factors. Differences in galaxy size, gas content, star formation rate, past mergers, galaxy type, and cosmic history. This is why estimates vary so much. The universe is not simple, it is not uniform, it is a dynamic system where stars are constantly being created and destroyed, where galaxies grow and fade, and where cosmic history writes itself in the light of billions of suns. The bottom line is clear. The universe contains so many stars because galaxies have spent billions of years acting as massive star factories. Each galaxy contributes differently, but together they produce a cosmic population so large that numbers lose meaning. And even though star formation has slowed today, the stars already created will shine for billions or trillions of years, filling the universe with light long after new star birth becomes rare. Before we even try to count all the stars in the universe, we have to confront a simple truth. We cannot accurately count the stars in our own galaxy. The Milky Way surrounds us, holding hundreds of billions of stars, yet we see only a tiny fraction of them. Dust clouds block our view. Distances stretch too far. Stars blend together. Light fades before it reaches us. Even with the best telescopes, the Milky Way hides most of its population. Understanding why counting our own stars is so difficult reveals why estimating stars across the entire universe becomes one of the most challenging tasks in science. One of the biggest obstacles is dust, massive clouds of cosmic dust drifting between stars. These dust clouds absorb and scatter visible light, making it impossible to see what lies behind them. The Milky Way's disk is filled with such clouds, stretching across the night sky as the faint white band we call the galactic plane. To our eyes, that band looks bright and full of stars. In reality, it hides enormous sections of the galaxy. Behind the dust are regions packed with stars we cannot see. The centre of the Milky Way is the most extreme example. It contains some of the brightest and densest star clusters, but the dust between us and the core blocks most of the visible light. For centuries, we did not even know how large the Milky Way was because the dust fooled us into thinking the galaxy was much smaller than it truly is. Infrared telescopes help us see through some of this dust. Infrared light can penetrate dusty regions more easily than visible light. When astronomers observe the Milky Way in infrared wavelengths, a more complete picture appears. But even infrared imaging has limits. Some regions remain too dense or too distant, hiding stars from view. This creates uncertainty. No matter how advanced our equipment becomes, there will always be parts of the galaxy we cannot see directly. Another challenge is distance. The Milky Way spans more than 100,000 light-years across. Even with powerful telescopes, distant stars appear extremely faint. Stars on the far side of the galaxy can be so dim that they blend into background noise. They're too far away to measure accurately. We cannot determine their exact brightness, location, or type. Counting stars at these distances becomes more like guessing patterns than observing objects directly. Stars also vary dramatically in brightness. Some stars shine brightly and can be detected from across the galaxy. Others are so faint that even nearby examples are difficult to see. Red dwarfs, the most common type of star in the galaxy, are extremely dim. A single red dwarf is easy to miss if it lies behind any amount of dust or at a moderate distance. Even though red dwarfs make up the majority of stars in the Milky Way, many remain undetected. This makes direct star counts nearly impossible. We cannot simply look at the sky and tally them. We must estimate based on what we can see and on models of stellar populations. Binary and multiple star systems add another layer of complexity. Many stars do not exist alone. They orbit each other in pairs, triples, or even larger groups. Some stars are so close together that from Earth they appear as a single point of light. Others orbit so far apart that we cannot easily measure which stars belong to which systems. This makes identifying individual stars complicated. When we count what looks like a single star, it may actually be 2 or 3 stars orbiting one another. This inflates uncertainties and makes precise counts harder. The structure of the Milky Way also contributes to the difficulty. Our galaxy contains several main components: the central bulge, the thin disk, the thick disk, the halo, and various star clusters. Each of these regions holds stars of different ages, brightness levels, and densities. The bulge contains tightly packed old stars. The disk contains younger stars and regions of active star formation. The halo contains ancient stars spread across an enormous volume. Each region requires a different method of measurement. The Milky Way is not a simple structure. It is a layered, dynamic, complex system. Even our position inside the galaxy makes counting difficult. Because we are inside the disk, we cannot see the entire galaxy from an outside perspective. It's like trying to count all the trees in a forest while standing on the ground between them. Trees nearby are easy to count. Trees far away blend together. Hills and valleys hide sections. The forest seems endless. From within the galaxy, the view is similarly limited. We can map certain regions, but we cannot see the whole structure clearly. We must piece together our understanding from limited angles and fragments of data. Another challenge comes from stellar evolution. Stars are born, live, and die. Massive stars explode as supernovae. Smaller stars quietly fade into white dwarfs. Some stars lose mass, shedding material into space. Others gain mass from companions in binary systems. The Milky Way star population is constantly changing. When we estimate the number of stars today, we count not only luminous stars, but also dead and dying ones. But detecting faint white dwarfs or neutron stars hidden in dust clouds is extremely difficult. Many remnants remain invisible to our instruments. This means our tally must include large margins of uncertainty. The Gaia mission, launched by the European Space Agency, has improved our understanding dramatically. Gaia measures the position, distance, and motion of over 1 billion stars with incredible precision. It has given us the most detailed map of the Milky Way ever created. But even Gaia captures only a fraction of the galaxy. 1 billion stars is impressive, but the Milky Way likely contains hundreds of billions. Most stars remain beyond Gaia's reach due to distance, dust, or faintness. Gaia gives us a powerful sample, but we still rely on extrapolation to estimate the total. Astronomers use models to fill in the gaps. They study small, well-measured regions of the galaxy and apply statistical methods to estimate how many stars exist in similar regions elsewhere. They measure star densities in different parts of the disk. They estimate the total mass of the galaxy and determine how much of that mass belongs to stars. These methods provide a range of estimates rather than exact numbers. The Milky Way is often said to contain between 100 billion and 400 billion stars. But the true number may be higher or lower. We cannot know for sure. Another complication arises from hidden star populations. Brown dwarfs, objects larger than planets but too small to ignite as stars, float throughout the galaxy. They emit little light and are extremely difficult to detect. The Milky Way may contain billions of them, but we cannot count them accurately. They blur the line between what we consider stars and what we consider substellar objects. Some estimates include them, others exclude them. This inconsistency further widens the uncertainty in our total count. Star clusters also complicate the picture. The Milky Way contains thousands of open clusters and hundreds of globular clusters. Each cluster holds anywhere from a few dozen to millions of stars, but clusters vary in brightness and size. Some are easy to detect, others are faint and lost within the background of the galaxy, because clusters represent concentrated regions of stars. Missing a cluster means missing a large number of stars. As we find new clusters, our estimates of the total star count shift again. The galaxy's halo is another difficult region. It stretches far beyond the disk and contains ancient stars spread thinly across a vast region. These stars are faint, far apart, and difficult to detect. The halo may contain many more stars than we currently know. Because of its immense size, even a low density of stars adds significantly to the total. Yet the halo remains one of the most mysterious regions of the Milky Way. All these factors combine to make counting stars in our own galaxy a complex and uncertain task. We cannot list each star individually. We cannot photograph them all. We cannot see through dust or measure faint stars at great distances with perfect accuracy. Instead, we make estimates based on observable data, statistical models, and careful comparisons. These estimates give us a general picture. The Milky Way contains hundreds of billions of stars, but the precise number remains out of reach. This uncertainty becomes important when we scale up to the entire universe. If we cannot count stars in a single galaxy, the galaxy we live in, then counting stars across hundreds of billions or trillions of galaxies becomes a challenge of unimaginable scale. Yet astronomers continue to refine methods and improve observations, pushing closer to understanding the true population of stars. Estimating the total number of stars in the universe requires combining everything we know about galaxies, cosmic structure, star formation, and the limits of our own observations. It is one of the largest calculations humanity has ever attempted because it involves quantities far beyond ordinary experience. We cannot count stars one by one, or even galaxy by galaxy. Instead, scientists use a set of indirect methods that rely on what we can observe and what we know about how galaxies behave. These methods involve assumptions, approximations, and careful modelling. But even with all these tools, the final number we arrive at feels less like a count and more like a glimpse into something too vast to imagine. The first step in estimating the total number of stars is determining how many galaxies exist. Thanks to deep field images and modern telescopes, we know that the observable universe contains hundreds of billions and possibly trillions of galaxies. But galaxies differ widely in size and mass. Some contain a few million stars, others contain hundreds of billions. Some rare giants contain trillions. Because galaxies are so diverse, we cannot simply multiply the number of galaxies by a single average number of stars. The average varies depending on how we weigh the contributions of giant galaxies versus dwarf galaxies. Large galaxies dominate the mass of the universe, but dwarf galaxies dominate in sheer number. This dynamic complicates any effort to estimate a straightforward average. Scientists begin by grouping galaxies according to type: spirals, ellipticals, irregulars, dwarfs, ultra-compact dwarfs, and others. Each category tends to have a characteristic range of star counts. For example, spiral galaxies like the Milky Way usually contain around 100 to 400 billion stars. Elliptical galaxies can contain far more, sometimes over 1 trillion stars. Dwarf galaxies typically contain a few million, while ultra-faint dwarfs may contain only a few thousand. By combining these known distributions with the estimated number of each galaxy type in the universe, scientists can calculate a weighted average number of stars per galaxy. But even this approach has uncertainties. Many galaxies are too faint to categorize. Others are so distant that we cannot determine their type. Some galaxies are hidden behind brighter nearby objects. Others blend into the cosmic background. This means our estimate must include assumptions about unseen galaxies. We know that many galaxies exist beyond current detection limits, because gravitational lensing and deep infrared imaging reveal objects that were invisible before. Each discovery implies that more galaxies are hiding in the darkness, quietly adding to the universe's total star count. Once we have a rough average number of stars per galaxy, scientists multiply it by the estimated number of galaxies in the observable universe. If we assume around 200 billion galaxies, and if each galaxy contains roughly 100 billion stars on average, the result is a number around 20 sextillion stars, a 2 followed by 22 zeros. But if we assume 2 trillion galaxies, and if we adjust the average to include dwarf galaxies more accurately, the estimate climbs into the range of 100 sextillion to 1 septillion stars. These numbers vary depending on assumptions, but they always end in a staggering conclusion. The universe contains far more stars than anything we could hope to count directly. Scientists also consider the matter density of the universe, measured by analysing how galaxies cluster and how dark matter shapes cosmic structure. By estimating the total mass of the universe and subtracting the mass attributed to dark matter and dark energy, scientists can estimate the amount of baryonic matter, the normal matter that forms stars. By determining what fraction of baryonic matter exists in stars, they derive another estimate for the total star mass. Dividing that mass by the average mass of a star gives another estimate for the total number of stars. This method is more indirect but helps confirm calculations based on galaxy counts. Another method involves luminosity, the total brightness of galaxies across the observable universe. By measuring the total light output from large samples of galaxies and comparing that with the known brightness range of different types of stars, astronomers can estimate how many stars exist to produce that light. This method faces challenges because galaxies contain dust that absorbs light and re-emits it in infrared radiation. Still, with modern instruments that observe in multiple wavelengths, astronomers can estimate total stellar luminosity more accurately than ever before. Star formation rates also help refine estimates. Scientists know how quickly galaxies formed stars in the early universe and how the rate has changed over time. By modelling the history of star formation, they can estimate how many stars must exist today as a result of billions of years of stellar birth. This method provides a cumulative view, tracking star formation across cosmic time. It helps fill in the gaps for galaxies too faint or too distant to observe directly. Even though all these methods produce wildly large numbers, none can produce a precise total. The universe is too big, too complex, and too full of hidden regions. There are galaxies behind other galaxies. There are galaxies too faint to detect. There are galaxies whose light has not reached us yet. The observable universe is only a part of the entire universe, and the true star count could be far larger. Yet even focusing only on the observable universe gives us a number so immense that it changes our perspective completely. One way to grasp the scale is to compare stars with grains of sand. If every star in the observable universe were a grain of sand, you would fill beaches, deserts, oceans, and continents many times over. You would bury entire worlds under hills of sand. The comparison is imperfect, but it communicates one essential truth. The universe produces stars on a scale that goes beyond comprehension. Another perspective comes from the idea that the universe might be infinite. If space stretches endlessly, then the number of galaxies and stars is also infinite. In that case, any attempt to count stars becomes meaningless. We are looking at an endless field of cosmic light that extends forever. Even if the universe is finite, the regions beyond the observable horizon may contain many more galaxies than we see. Light from those galaxies has not had time to reach us. They remain hidden, but they exist. If we include them, the star count grows far beyond anything we can estimate. Wherever we look, the universe reveals abundance. Even tiny patches of sky, when magnified deeply enough, show thousands of galaxies. Each galaxy contains millions or billions of stars. Each star system may hold planets. Some planets may hold life. Some may hold entire ecosystems. The sheer number of stars suggests that the universe is not empty or rare. It is overflowing with opportunities. But despite all these enormous numbers, one thing remains clear. Our attempt to count stars is not about finding an exact total. It is about understanding the scale of the universe and seeing our place within it. Even if the final number never becomes exact, the act of estimating it teaches us about cosmic structure, star formation, galaxy evolution, and the limits of human perception. The universe humbles us by showing how small we are, but it also reminds us how remarkable it is that we can even ask such questions. Every star we estimate represents something real, a burning sphere of gas far away, shining through the darkness, part of the grand architecture of the cosmos. When we say there are sextillions or septillions of stars, we are not exaggerating. We are trying to communicate the unthinkable scale of a universe that refuses to be simple. When we talk about how many stars exist in the universe, we usually refer to the observable universe, the part of the cosmos we can see. But what we can see is limited by the speed of light and by the age of the universe itself. Light takes time to travel. The farther away an object is, the longer it takes for its light to reach us. The universe is about 13.8 billion years old, but because space has expanded during that time, the farthest galaxies we can see today are not 13.8 billion light years away. They're around 46 billion light years away in every direction. This forms a spherical bubble around us, a cosmic horizon beyond which we cannot observe. Everything inside the sphere is the observable universe. Everything outside it is still invisible. This boundary is not physical. It does not block anything. There is no wall or edge. The horizon exists only because we cannot receive light from beyond it. Light from those regions has not had enough time to reach us. As the universe continues to expand, more distant regions move away faster than their light can travel toward us. This means the observable universe will always remain limited. No matter how advanced our technology becomes, no telescope will ever see beyond this horizon. We are permanently confined to a cosmic bubble determined by the laws of physics and the passage of time. Understanding this boundary is crucial because when we estimate the number of stars in the universe, we are only counting the stars inside this observable sphere. We do not know how large the entire universe is. It may be much larger than the observable region. It may stretch far beyond our horizon. It may even be infinite. If the universe is infinite, then the number of stars is also infinite. But even if it is finite, it could still be massively larger than the part we can observe. This means the star count we estimate, already enormous beyond comprehension, could represent only a tiny fraction of the real number. The observable universe contains galaxies spread across space in a giant cosmic web, but this web almost certainly continues beyond what we can see. Imagine standing in a forest at night with only a small lantern. Everything illuminated by the lantern represents the observable universe. You can count the trees within that circle of light, but the forest continues much farther, stretching into darkness. You cannot see it, but you know the forest does not end at the edge of your lantern. The observable universe works the same way. The galaxies we see are only the ones close enough for their light to reach us. Beyond that horizon, the cosmic forest continues. The expansion of the universe makes this even more complicated. As space expands, distant galaxies move away from us. The farther away they are, the faster they recede. Some galaxies are moving away faster than light, not because they're travelling through space that fast, but because the space between us and them is expanding. This does not break any law of physics, but it does mean their light will never reach us. They are forever beyond observation, even though they exist. The universe may contain countless galaxies forever locked outside the observable region, hidden not because they're faint, but because of cosmic expansion. When we estimate star counts, we focus only on the galaxies within the observable universe, but the galaxies outside it remain part of reality. Their stars, planets, and possible life forms exist independently of our ability to see them. The universe does not shrink simply because we lack the ability to observe certain regions. This means every number we use, hundreds of billions of galaxies, sextillions of stars, may be only a fraction of the true total. Scientists use cosmic inflation theory to understand what might exist beyond our observable region. Inflation describes a rapid expansion of space fractions of a second after the Big Bang. This expansion was so extreme and so powerful that it smoothed out the universe on large scales. If inflation continued for even slightly longer than we think, the universe could be vastly larger than the observable portion. It could be millions, trillions, or quadrillions of times larger, or it could be effectively infinite. Even conservative estimates suggest that the observable universe is only one small bubble in an enormous cosmic sea. Some models propose that the observable universe is like a tiny pixel in an image so big we cannot see the edges. Others suggest that our observable region is just one pocket in a multiverse of countless other regions, each with its own galaxies, stars, and possibly even different physical laws. While these ideas remain theoretical, they emphasize how limited our view is. The night sky feels huge, but scientifically speaking, it represents only a small sample of reality. Another way to understand the limits of the observable universe is through cosmic look-back time. When we look at distant galaxies, we see them as they were billions of years ago. Light from a galaxy 40 billion light-years away may have left that galaxy when it was still forming its first stars. Today, that same galaxy might contain far more stars than we can observe, or it might have merged with other galaxies to form something even larger. Much of what we see is not the universe today, but the universe as it was in the past. This means our estimates of star populations must account for the fact that the galaxies we observe have evolved beyond the snapshots we see. Even within the observable universe, much remains hidden. Dust obscures galaxies. Distance dims them. Some galaxies blend into background noise. Others lie behind brighter galaxies, making them difficult to detect. Every new telescope reveals more of them, pushing our limits farther. But no matter how far we push, the universe always extends beyond our reach. This is why the observable universe represents not just a physical limit, but a philosophical one. It reminds us that our knowledge is always incomplete. It forces us to accept that what we see is not all that exists. The cosmos is grander than our senses, broader than our tools, and deeper than our understanding. The boundary of the observable universe is a reminder that we are still in the early stages of exploration. Despite these limitations, the observable universe gives us enough information to understand the scale of the cosmos. With every galaxy we see, we infer the existence of more beyond it. With every star we count, we imagine the countless others that lie unseen. The horizon does not frustrate us, it inspires us. It reminds us that the universe is vast, abundant, and full of mysteries waiting to be uncovered. The concept of an observable universe also shows us how connected everything was in the beginning. Before the expansion, the entire observable region was smaller than a grain of sand. Everything we see today, hundreds of billions of galaxies, was once compressed into an unimaginably tiny space. This expands our appreciation for how the universe grew into its current form, and why so many stars exist today. When space expands on such a scale, the number of stars it can hold becomes enormous. Scientists continue refining models of the entire universe, exploring whether it is finite or infinite. If the universe is finite, its size may be unimaginable. If it is infinite, then counting stars becomes conceptually meaningless. Either way, the observable universe is only a piece of the puzzle. The true cosmic population of stars likely dwarfs our highest estimates. This realization changes how we see ourselves. We often look up at the night sky and feel small, surrounded by countless stars. But the reality is even more overwhelming. The stars we see are not countless, they're only a local sample. The true number of stars across the whole universe, observable and beyond, surpasses anything WCPC can estimate. The light that reaches us tells only part of the story. The number of stars in the universe is not fixed. It changes constantly because stars are born, grow, evolve, and eventually die. Their life cycles affect how long they shine, how many new stars they help create, and how the universe recycles their material. To understand why the universe holds so many stars today, we have to understand how stars live and how they die. Their lifespans vary wildly, from millions of years to trillions, shaping the cosmic population over time. Some stars vanish quickly, while others remain shining long after galaxies stop forming new stars. These differences influence the total number of stars present in the universe at any moment. Stars begin their lives in cold, dark clouds of gas. When gravity pulls these clouds together, new stars ignite at their centers. But the size of the newborn star determines almost everything about its future. Massive stars live fast and die young. Small stars live slowly and endure for unimaginable lengths of time. These contrasting lifespans create a universe filled with both ancient stars still burning and the remnants of others that died long ago. The largest stars are rare but extremely powerful. They burn through their nuclear fuel rapidly, shining intensely for millions of years before collapsing in spectacular explosions called supernovae. During their short lives, they influence entire regions of their galaxies. Their intense radiation shapes surrounding gas clouds. Their explosions seed space with heavy elements. Even though massive stars contribute to the universe's beauty and complexity, they do not last long enough to increase the number of stars significantly. Their short lives mean that at any given time, only a small number exist. They come and go quickly, adding little to the long-term population. In contrast, small stars dominate the universe simply because they live so long. Red dwarfs, the smallest stars, burn slowly and steadily. They consume their fuel at a pace that allows them to live for trillions of years. Since the universe is only 13.8 billion years old, not a single red dwarf has ever died. Every red dwarf ever formed is still shining today. This is one of the reasons star counts are so enormous. Billions of small stars continue to accumulate generation after generation without disappearing. Even if star formation eventually stops, these red dwarfs will continue to shine far into the distant future, long after the universe has moved on from its star-forming era. Medium-sized stars like our Sun fall somewhere in between. They live for billions of years, long enough to host planets and give lifetime to evolve. After consuming their hydrogen fuel, they swell into red giants, shed their outer layers, and leave behind white dwarfs, dense, cooling stellar cores that slowly fade over billions of years. While these stars do not explode dramatically, their gentle deaths also contribute to future star formation. The gas they shed becomes part of the interstellar medium, recycling into new stars over time. Even white dwarfs, though dim and difficult to detect, add to the universe's star count. They represent stars in their final stages, no longer shining brightly, but still present. The galaxy contained countless white dwarfs, many hidden in dust or too faint to measure easily. They increase the total number of stellar objects, even though their light barely reaches us. Neutron stars and black holes, the remnants of massive stars, also complicate the picture. Although they are not stars in the traditional sense, they are stellar leftovers that must be accounted for when estimating how many stars once existed. Neutron stars are incredibly dense, spinning rapidly and emitting beams of radiation. Black holes formed from the collapse of the most massive stars are invisible but exert strong gravitational influence. These remnants do not shine like normal stars, but they represent the end stages of stars that once contributed to the universe's brightness. The balance between star birth and star death determines the total number of stars at any given time. Early in the universe, star formation rates were extremely high. Galaxies were young, filled with gas and forming stars rapidly. Many of the stars created in that era still shine today. As time passed, gas supplies decreased and star formation slowed, but the long-lived stars remain. The universe today contains stars from every era. First-generation stars that formed shortly after the Big Bang, mid-age stars like the Sun, and countless young stars still emerging in star-forming regions. This accumulation explains why the star count is so enormous. Even though massive stars die quickly, the vast majority of stars live for billions or trillions of years. The universe keeps adding stars to its total while losing relatively few. Over cosmic time, the number of stars increases steadily. The star formation rate has decreased dramatically since its peak, but the legacy of earlier star formation remains in the countless stars still shining. The recycling of material also plays a crucial role. When stars die, their gas does not disappear. It returns to space, enriched with elements created during stellar fusion. This enriched gas cools more efficiently, helping new stars form more easily. As a result, each generation of stars spawns new generations, continuing the cycle. Star death does not reduce the universe's star count in the long run. It contributes to the formation of more stars. The universe is a massive recycling system, constantly turning old stars into new ones. Cosmic time also influences the distribution of stars. Early generations of stars were mostly massive because the universe lacked heavier elements. Later generations contained more small and medium-sized stars because heavier elements allowed gas to cool more effectively. This shift increased the proportion of long-lived stars, helping the universe accumulate even more stars over time. The population of long-lived red dwarfs continues to grow, shaping the overall star count in a profound way. Some stars form in clusters, and some clusters dissolve over time, distributing their stars across galaxies. Other clusters remain intact for billions of years, preserving their ancient stars in tight formations. These clusters contribute to the total number of stars and reflect the history of star formation across cosmic time. Even though clusters eventually spread out, the stars they contain continue to add to the universe's population. Binary star systems also impact the star count. Many stars form in pairs. Some exchange mass, some merge, some explode. These interactions influence how many stars survive, how many new stars form, and how the population evolves. But overall, binary systems contribute to the richness of the stellar population rather than reducing it. As the universe continues to expand, star formation will eventually slow to a near halt. Galaxies will run out of gas, and the cosmic supply of star-forming material will decrease. But even then, the vast number of existing stars will remain. Small stars will shine for trillions of years, long after star birth becomes rare. This means the star count we estimate today reflects not just the universe's past, but also its long future. The universe is in a long era of stellar light, supported by stars that endure for extraordinary spans of time. This long-lived population ensures that the universe remains full of stars, even as the rate of new star formation declines. When we count stars today, we're counting the accumulation of billions of years of cosmic history. Each star represents a chapter in that story, each one formed under unique conditions shaped by gravity, chemistry, and time. The life cycles of stars show why the universe contains so many of them. They are created efficiently. They live for extraordinary lengths, and even when they die, they leave behind remnants that contribute to future generations. The cosmic population grows because most stars never truly leave the stage. They continue shining or cooling or influencing their surroundings long after their active lives are over. The universe does not create stars in a uniform way. Every galaxy forms stars according to its own history, structure, and environment. This is why two galaxies of similar size can contain wildly different numbers of stars. Some galaxies overflow with bright young stars. Others are quiet, filled mostly with old fading ones. Some galaxies barely form stars at all. Others form stars so rapidly that their brightness outshines entire regions of space. Understanding this diversity is essential because it shows why estimating the total number of stars in the universe is so complicated. Each galaxy follows its own path, shaped by billions of years of cosmic events. One of the biggest factors shaping a galaxy's star population is how much gas it has. Gas is the raw material from which stars form. If a galaxy collects a large supply of hydrogen and helium, it can create stars continuously. Spiral galaxies, for example, contain swirling disks full of cold gas. Their spiral arms act as engines, compressing gas and triggering the birth of new stars. This is why galaxies like the Milky Way have active star-forming regions scattered throughout their arms. A steady supply of gas means a steady supply of new stars. Elliptical galaxies tell the opposite story. They may be large, bright, and massive, but most of their stars formed long ago. Today, ellipticals contain very little cold gas. Without gas, no new stars can form. These galaxies shine mostly through the light of old stars that were born billions of years ago during violent bursts of star formation in the past. Their star populations are huge but stagnant. They contribute a massive number of stars to the universe, yet their current star-forming activity is almost non-existent. This contrast between spirals and ellipticals shows how history determines a galaxy's current behaviour. Dwarf galaxies contribute another layer of complexity. These small galaxies contain far fewer stars, often ranging from a few million to a few hundred million. But what they lack in size, they make up for in numbers. Dwarf galaxies are the most common type in the universe. Their sheer abundance means they contribute significantly to the total star count. Yet each dwarf galaxy is different. Some form stars slowly over long periods. Others experience bursts of star formation when triggered by nearby galaxies. Some lose gas early, limiting their star populations. Others gather gas from their surroundings and grow steadily. This diversity inside a single category of galaxies makes estimating star populations even harder. Interactions between galaxies create more differences. When galaxies pass near one another, their gravitational forces distort one another's shapes. These tidal interactions can pull gas into new regions, creating waves of star formation. Some galaxies undergo complete mergers. When two galaxies collide, gas clouds crash together, compressing violently and creating intense bursts of star formation. These starburst events can produce hundreds or thousands of new stars at once. Galaxies involved in such collisions often contain mixed populations, old stars from before the collision and young stars born during the merger. Over time, the galaxies settle into new shapes, with star populations shaped by the events they experienced. Galaxy clusters also influence star populations. In a cluster, galaxies are packed closely together and move rapidly through hot, dense gas. This environment can strip gas from galaxies through a process called ram pressure stripping. When a galaxy loses its gas, it loses its ability to form new stars. Many cluster galaxies become quenched, filled with old stars, unable to produce new ones. Meanwhile, galaxies at the edges of clusters may gather gas and form stars more easily. This uneven distribution of gas within clusters produces galaxies with very different star populations despite living in the same region of space. Another factor that influences star populations is metallicity, the abundance of heavier elements in a galaxy. Early in the universe, galaxies contained only hydrogen and helium. This made star formation difficult, and the first stars were extremely massive. As generations of stars lived and died, they enriched galaxies with heavier elements like carbon, oxygen, and iron. These heavier elements help gas cool more efficiently, allowing smaller and more stable stars to form. Galaxies with high metallicity tend to produce a greater variety of stars, including long-lived red dwarfs. Galaxies with low metallicity still produce stars, but often in different proportions. This variation affects how many stars galaxies can create and how long those stars live. Even the shape and internal structure of galaxies matter. Spiral galaxies have organized patterns that guide gas into dense regions where stars can form. Ellipticals, shaped by past collisions, lack this structured flow of gas. Irregular galaxies, often distorted by nearby gravitational forces, may form stars unpredictably. Many irregular galaxies show areas of intense star formation next to regions with almost no stars. Their chaotic structures lead to chaotic star populations. The age of a galaxy also influences its star count. Younger galaxies still contain large amounts of gas, allowing them to form stars rapidly. Older galaxies may have used up or lost much of their gas. They may contain many stars, but those stars are mostly ancient. The universe today contains galaxies from different eras, some just beginning to form stars, others nearly finished. This mix creates a wide range of star populations across the cosmos. Some galaxies form ultra-dense central cores, with millions of stars packed into a small region. Others develop extended halos, where stars spread thinly across vast distances. Some contain giant molecular clouds, where stars form in clusters. Others contain almost no clouds at all. The internal layout of a galaxy determines where stars can form and how they spread over time. Dark matter also shapes galactic star populations. A galaxy with a massive dark matter halo can hold onto gas more easily, allowing star formation to continue. A galaxy with a weaker halo may lose gas quickly through supernova winds or tidal forces, limiting its star population. Dark matter acts as the gravitational framework that holds galaxies together, and its distribution influences everything from star formation to galaxy growth. Scientists study these differences to estimate how many stars galaxies contain. But because galaxies vary so much, creating a universal estimate is extremely challenging. A galaxy the size of the Milky Way might contain a few 100 billion stars. A dwarf galaxy might contain only a few million. A giant elliptical might contain several trillion. When we attempt to estimate the total number of stars in the universe, we must account for this extraordinary range. This is why the star count cannot be expressed with precision, because the universe does not produce stars uniformly. Another challenge comes from hidden galaxies. Many galaxies are faint, obscured by dust, or located behind brighter ones. These galaxies often contain older or dimmer stars that contribute significantly to the total population. Modern telescopes reveal more of these faint galaxies each year. As we detect more of them, our estimates of the universe's total star count rise again. Every improvement in technology shows us that the cosmos contains more stars than we previously believed. The diversity of galaxy environments, histories, and structures creates a universe filled with star populations that cannot be summarized easily. Some galaxies create stars quickly, others slowly, and others not at all. Some environments encourage star formation, others shut it down. Over billions of years, these interactions produce a cosmic landscape filled with stars of every type and every age. And yet, despite the complexity, one pattern emerges. The universe produces a staggering number of stars because galaxies, no matter their size or shape, almost always find ways to create them. Gas collapses, gravity pulls, stars ignite. The details vary from galaxy to galaxy, but the outcome is the same. Light fills the universe. To understand why the universe contains so many stars today, we have to look back to the very beginning, long before galaxies became the majestic structures we see today. The first stars, the earliest lights to ignite after the cosmic dark ages, played a crucial role in shaping everything that followed. These ancient stars, known as population 3 stars, were different from any stars we see today. They were larger, hotter, brighter, and far more short-lived. And even though none of them survive today, their influence echoes through the structure of the entire universe. By shaping the chemistry, the temperature, and the distribution of matter, they made the universe capable of forming the vast population of stars we see now. The early universe contained only hydrogen and helium. There were no heavier elements like oxygen, carbon, iron, or nitrogen, elements that are essential for cooling gas clouds and forming smaller stars. As a result, the first stars could not form in the same way modern stars do. Without heavy elements to help gas cool and condense efficiently, early gas clouds collapsed into enormous masses. These masses ignited into stars that were hundreds of times more massive than our Sun. Their lifespans were incredibly short, lasting only a few million years, an instant on cosmic timescales. These first stars were so luminous that they transformed their surroundings. Their radiation heated nearby gas and prevented other stars from forming too quickly. Their ultraviolet light ionized hydrogen throughout the universe, ending the cosmic dark ages. Their brilliance carved out bubbles of hot gas, shaping the early structure of galaxies. But their most important contribution came at the end of their lives. When these massive stars exploded as supernova, they seeded the universe with the first heavy elements. These elements spread into space, enriching gas clouds and enabling the formation of future generations of stars. It was these heavy elements, carbon, oxygen, neon, silicon, iron, that allowed smaller, longer-lived stars to form. With heavier elements mixed into the gas, the next generation of stars could cool more efficiently, condense more easily, and take on a wider range of sizes. This shift transformed star formation forever. It allowed the universe to produce the enormous number of stars we see today. Without the first stars enriching the cosmos, later stars like the Sun could not have formed. Planets could not have formed. Life could not have formed. The universe would have remained full of massive, short-lived stars and little else. The first stars also influenced how galaxies grew. Their supernova explosions created shockwaves that compressed gas, triggering bursts of star formation. At the same time, they pushed gas away in some regions, delaying star formation in others. This push and pull dynamic shaped the early architecture of galaxies. Some regions became dense with stars, others remained empty for long periods. Over time, the enriched gas gathered into rotating disks, forming the first spiral galaxies. These galaxies would later become fertile environments for ongoing star formation, contributing billions of stars to the overall count. Even though the first stars died long ago, their chemical fingerprints remain. When scientists study ancient stars in the Milky Way's halo, they find elements produced by the first generation of stars. These ancient stars contain lower amounts of heavy elements than modern stars, but enough to show that they were born from gas influenced by the earlier supernova. In this way, the first stars left behind clues that allow astronomers to reconstruct the early universe and understand how the star population grew over time. The first stars also influenced the temperature of the universe. Their intense radiation heated surrounding gas, making it harder for new stars to form immediately. This may sound like a slowdown, but it actually helped shape galaxies more efficiently. As gas cooled and settled over time, it formed stable structures that supported long-term star formation. Instead of collapsing chaotically into massive stars, enriched and cooled gas clouds could form a mix of small and medium-sized stars. These stars, especially the small ones, outnumber the early massive stars dramatically. They filled the universe with long-lived light sources, building toward the massive star count we estimate today. As galaxies assembled and dark matter halos grew, star formation became more organized. The enriched gas gathered in the centers of halos, collapsing into dense regions where stars could form continuously. These early galaxies merged, collided, and grew, mixing their enriched gas and producing diverse star populations. Over billions of years, galaxies accumulated trillions of stars, forming the cosmic structures we now observe. The earliest stars also influenced the large-scale distribution of matter. Their radiation helped determine where gas would collapse into galaxies and where voids would remain empty. This shaped the cosmic web, the vast network of filaments and clusters that spans the universe. The cosmic web determined where star formation would be most intense and where galaxies would cluster densely. In regions with abundant early star formation, galaxies grew quickly. In regions with fewer early stars, galaxies remained smaller and produced fewer stars. These early differences continue to influence the distribution of stars across the cosmos today. Another important factor is the rate at which the universe formed stars. Shortly after the first stars appeared, the star formation rate began to rise. It reached its peak around 10 billion years ago. During this period, known as cosmic noon, galaxies were forming stars at extraordinary rates. Some galaxies produced hundreds or even thousands of stars per year. The universe was extremely active, filled with bright young stars. Much of the universe's total star population formed during this era. Although star formation has slowed dramatically since then, the stars created during cosmic noon still shine today. They make up a significant fraction of the galaxies we see. The first stars set the stage for all of this. Without their contributions, the universe would not have developed the conditions necessary for widespread star formation. They were the pioneers of cosmic evolution. They prepared the universe for everything that followed. Even though none survive today, their legacy remains in every galaxy, every star, every planet, and every molecule heavier than helium. The life cycle of the first stars also reveals why the universe contains so many long-lived stars now. Once heavy elements were available, the universe began producing vast numbers of red dwarfs, small stars that live for trillions of years. These stars accumulate over time, building a population that grows and never declines. The universe is filled with these tiny faint stars, each contributing to the overwhelming star count. The first stars allowed these long-lived stars to form in the first place. Even the way galaxies grow today echoes the early universe. When galaxies merge, their gas combines and star formation accelerates. These events add billions more stars to the cosmic total. But the ability of galaxies to form stars in such quantities traces back to the chemical enrichment caused by the first stars. They started the process and everything else followed from there. In this way, the first stars, though short-lived, are responsible for the vast population of stars that exist today. They shape the universe's chemistry, structure, and temperature. They influenced galaxy formation and star formation. They made it possible for long-lived stars to dominate the cosmos, and by doing so, they ensured that the universe would always contain an enormous, nearly incomprehensible number of stars. The universe is not finished creating stars, and it is not finished changing. The total number of stars we see today is only one chapter in a much longer story. Stars will continue to form, die, and transform the cosmos for trillions of years. The universe's future plays a major role in shaping how many stars will eventually exist. Understanding this future requires looking at how galaxies evolve, how gas supplies decline, and how long-lived stars continue shining far beyond the lifespan of the universe's brightest lights. The star count is not fixed. It is a moving target shaped by time itself. Right now, we live in a universe that is past its most active age of star formation. Billions of years ago, during the era known as cosmic noon, the universe produced stars at a rate far higher than it does today. Galaxies were younger, richer in gas, and constantly colliding. These collisions triggered massive bursts of star formation. Today, the universe is calmer. Many galaxies have already used or lost much of their gas. Star formation still occurs, but at only a fraction of its former speed. The total number of stars continues to rise, but slowly. The universe is entering a quieter, more stable phase. Over the next few billion years, star formation will gradually decrease even further. Galaxies like the Milky Way will continue forming stars from their remaining gas, but the supply is limited. Once the gas is consumed, star formation will slow to almost nothing. Some galaxies may experience new bursts of star formation when they collide, but even galaxy mergers will eventually stop producing significant new stars because future galaxies will contain less and less gas. The universe is running out of the raw material needed to create new generations of stars. Despite this slowdown, the total number of stars in the universe will continue increasing for many billions of years. Long-lived stars such as red dwarfs will outnumber all other stars by a huge margin. These small stars burn their fuel so slowly that they will shine for trillions of years, far longer than the universe has existed so far. Their longevity ensures that the universe will remain full of stars long after brighter stars, like the sun, have faded away. This population of red dwarfs will dominate the future of the cosmos, becoming the primary contributors to the star count. The universe's expansion also influences future star formation. As space expands, galaxies drift farther apart. Over extremely long periods, this expansion will isolate galaxies from one another. They will no longer collide or interact. Without collisions, bursts of new star formation will become rare. Each galaxy will remain alone in an ever-growing darkness. Within each galaxy, the remaining gas will eventually condense into smaller and smaller pockets of star formation until the supply runs out entirely. But even when star formation stops, the stars already created will continue shining for ages. Medium-sized stars like the Sun will become red giants, shed their outer layers and turn into white dwarfs, dense cooling remnants that can glow for billions of years. Massive stars will continue exploding as supernova, creating neutron stars and black holes. These remnants add complexity to the universe, but do not add new light. Instead, they contribute mass to the galaxy, altering its long-term evolution. One of the biggest influences on the future star count comes from the red dwarfs. Because they burn fuel so slowly, they will dominate the galaxy long after more massive stars have disappeared. Even when galaxies stop forming new stars, the existing red dwarfs will remain active. Their slow and steady glow will be the primary source of starlight for trillions of years. As the universe ages, the night sky from any surviving planet will become dimmer and redder, illuminated mostly by these small faint stars. Eventually, even red dwarfs will begin to die, but this process will take far longer than the current age of the universe. Some red dwarfs will survive for 50 trillion years or more. Their deaths will produce white dwarfs that continue cooling slowly. The universe will shift from a place dominated by active stars to a place dominated by stellar remnants, white dwarfs, neutron stars, black holes, and brown dwarfs. Light will become scarce, but these objects will still exist, contributing to the total count of stellar bodies. Over extremely long time scales, star formation may not stop entirely. Some gas will remain trapped in molecular clouds, slowly condensing under gravity. In isolated pockets, new stars may form even after the main era of star formation has ended. These late-generation stars will be rare, but they will show that the universe never stops evolving completely. The number of stars will continue to rise, but at a pace too slow to compare with earlier cosmic history. In the far future, galaxies themselves will transform. Some will merge with neighbours, some will be torn apart by gravitational forces, others will survive as isolated islands, floating in expanding space. Over trillions of years, these galaxies will contain mostly old stars and stellar remnants. But because so many of today's stars live for such long periods, the universe will remain full of billions upon billions of glowing objects. The population of stars will shift in type, but not in scale. The number of stellar objects will remain enormous. The universe's long-term future leads to a fascinating realization. The total number of stars continues increasing even as the universe grows darker. Because the most common stars live for such long spans of time, the universe becomes a place where the star count climbs while the visible light fades. The cosmos becomes a quieter place, but not an empty one. The stars remain even if their brightness declines. This future also shows why the number of stars is so difficult to define. Should we count only bright stars? Should we include brown dwarfs? Should stellar remnants count as part of the total? As the universe ages, these questions become more important because stellar remnants will eventually outnumber active stars. If we count every object that originated as a star, the number grows larger over time. If we count only shining stars, the number eventually decreases. The total depends on what definition we choose. One thing, however, will not change. The universe will always contain more stars than we can imagine. The processes that built the cosmic population, gravity, gas dynamics, stellar evolution, and cosmic expansion, ensure that the total number of stars is vast beyond meaningful comprehension. Whether the universe contains sextillions, septillions, or more, the number is so large that it will always push the limits of human understanding. The long future of the universe adds a sense of perspective to everything we observe today. The night sky we see now is temporary. The star count we estimate now is temporary. The universe is dynamic, evolving, and alive with change across unimaginable timescales. Our role is not to capture a final number, but to understand the processes that shape the cosmos. The number of stars will continue to grow, shift, and redefine itself long after humanity is gone. In the end, trying to count the stars in the universe is less about finding a final number and more about understanding the scale of everything around us. Every point of light in the night sky is part of a far larger story, one that stretches across time, across galaxies and across distances we can barely imagine. The stars we see are only a tiny fraction of what exists. Beyond them are billions of galaxies, trillions of suns, and a universe overflowing with light. And even with all our science, all our instruments, and all our knowledge, the universe remains bigger, richer, and more mysterious than anything we can measure. The true number of stars may be beyond counting, but the fact that we can even ask the question shows how far we've come. The night sky is not empty. It is a reminder that we live inside something vast, alive, and endlessly expanding, and our journey to understand it has only just begun.